Thank you very much for the invitation. So a few things. As you see, I don't have an association. I just work for myself nowadays, which has its advantages and disadvantages. It can be a bit nerve-wracking. So, then my philosophy is computers are first of all finite. So we don't necessarily have to consider infinity. And close enough is good enough. I started in numeric analysis, and if it's within epsilon, that's fine. And the last bit is everything comes down to matrix operations. Because if you think about computers only understand zeros and ones, then you can build numbers, then you can do operations on the numbers, and you can put the numbers into arrays. And that's everything else is just our interpretation, what the machine is doing. So when people say about general AI, it still comes down to just matrix operations. It's just very fast and a lot of them. So, but oh, I'm not good at topology, so you might have me there. So, yes, but the philosophy is keep things simple, because sometimes things are more complicated than we think, but sometimes things are simpler than we think. If you take the weather, you actually have a very good chance of being right if you just say the weather is just as it was yesterday. So just keep it simple. Now, the talk is about approximating data, modeling data, and there are several challenges in it. First one is we might encounter ill-conditioned matrices, which will be a problem. When we want to model the data, but keeping the model simple, but also explain the data adequately, that then means we have to choose a model space. Other thing is that nowadays data keeps arriving all the time. So we need to deal with that as well. If new data is arriving, then we want to update our model. We also would like to have some kind of confidence in our model predictions, because we are not good if we are completely off in our prediction. What would also be nice to know where we actually have to collect the data. So informed data collection, where is it most interesting to look for data? And another thing is limited computing power, up and down link capacity. Because we have very powerful computers all in our pockets, people do not quite think about it. But when I worked for the British Antarctic Survey, in Antarctica, you still have that problem. So you want to do things simply as possible. So, okay, then let's start going. So the data prediction problem is we have measurements T1 till TD, also known as targets. That's why it's a T. And these measurements depend on some parameters, x1 till xd. So it's a function which goes from a one space into the space of the targets. And D is now the dimension of our data space. It's just the number of data we have. And these quantities can be measured with more or less effort. Okay, so think about measuring in Antarctica. So, okay, but
the number of
no, that's just the number of them. X is a vector valued one, so it could be. Yes, T1 only depends on X1. Yes, thank you. Okay, yes. But then we also have that the measurements depend on parameters we do not know. And because real-world applications depend on factors which we cannot measure. So as an example, I always give the physics of waves. We really understand that. And a lot of stuff gets inferred by just sending sound waves through the ground, for example, and then listening to the reflection. What we don't know is what the ground is actually made up of. We don't know the material, we don't know the intersection of the materials, so that makes it then very complicated. And these are the unknown parameters of the process. Okay, so now the idea is if we have candidate functions, D1 till Dm, so that's now the model space. That's how many candidate functions we have. For example, we could have perfectly modeled sound waves going through one rock enclosed in other rock. So that's not a very complicated scenario. Somebody could model that. So we could do that and so on. And then we could just compare what these candidate functions give us to the data we are receiving. And yeah, we just do a linear combination of the candidate functions. And the thing is then that the coefficients, C1 till Cm, that's the ones we want to model. So, and the basis function, I say they are a dictionary, and they are just the building blocks out of which we want to build the model. And M is now the dimension of the model space, so how many we have there. Okay, then the relationship with the measurements is, well, Ti is just the function at xi, and then it's the linear combination of this. And if we want to write it in matrix form, well, we just have one matrix where each entry is evaluating one of the functions at a particular xi. And then T we summarize into one vector, we summarize it into one vector, and it becomes just a linear equation. Very easy, but just one thing to keep in mind. D is a D cross M matrix. It's called the design matrix. That's why I called it D. But D and M could not be static. D could vary with the number of measurements, and M could actually vary with the number of basis functions I'm choosing. So there we get some dynamic in it. And one very simple approach is we just minimize the sum of squares. So that's how we find C. That's long known. Gauss worked on it. And if you do it like undergraduates do, you just differentiate and set the gradient to 0. You can solve for C with that matrix equation. Okay. But the problem now is D transpose D might be ill-conditioned. It happens if your columns of D, which are just the functions evaluated, are too similar to each other. Where this can happen quite often is radial basis functions are very popular, and they depend on the distance of the point to the point where the function is centered. So if you have now two data points which are close to each other, the distance from the other data points will also be very similar. So these two columns end up very similar to each other, and we want ideally to avoid that. So one technique to avoid is with rich regression. You just add a multiple of the identity matrix to D transpose D to make sure it's not ill-conditioned. Other techniques is like what Ben Adcock is doing. He doesn't use least squares. He uses weighted least squares, which then again means the diagonal entries of that matrix, D transpose T, become dominant. And so then it's also not ill-conditioned. Another problem is overfitting. If we choose our model space too large, and then it can just, it allows a too close of a fit. And that also happens now in neural networks, where the universal approximation theorem says that if you give a neural network enough neurons, it can model any data. You just give it enough rope and it will hang itself. But the problem is it can hang itself because it models too closely. But then you get adversarial machine learning techniques, which then exploit that and can make the whole thing fall over. So
condition is not about.
Yes. Yeah. Yeah. So, but it depends in some way on the eigenvalues. So, yes. Okay. Yeah. Okay. So now the approach, which I like, is we assume that the measurements have noise. As I said, close enough is good enough. So, and most real life applications, there is some noise in it. So then we just add the noise to every, we assume there's noise resulting in every measurement. And normally the noise is just assumed to be identically normally distributed with some variance sigma squared. If you want to do it with outliers, which can happen as well, and so you just model it as a mixture of Gaussians, where one has the perhaps small sigma squared, but the other one can have a much larger variance or standard deviation. Or you can just do it uniformly in a range, which is then known as minimally informative. Okay, yes, and there's, if you want to know how to model a mixture, that's that paper. Okay, yes. So, and then we come to sparse Bayesian learning. The idea is that actually also the coefficients C follow a distribution. So, and how this distribution is modeled is we use the precision of a distribution, which is just the inverse of the, variance. I think so. So the thing is, if the precision is very, very large, that means that the distribution is actually peaked where we are predicting, and we are quite confident of that value of CM. If it remains large, then we say, well, we can't really say anything about it. So, okay. Yeah. So then you assume a multivariate prior distribution for the coefficient C, which is written up there. And A is just a diagonal matrix where the entries are alpha M, which is the precision of the distribution of the mth coefficient. And then you can calculate the posterior distribution just using Bayes, good old Bayes, and so on. And there you can see it has again tried to make this more stable by we now adding this matrix A in, and hopefully if we can invert it more easily then, okay? And that's then the mean of the posterior distribution mu. So we just need to do a few calculations to do that. Okay. So if I combine these things now, yes, there's the mu, it gets, yes, because there's a sigma to the -2 in front of that formula, you get a sigma squared A in there, and that is now, which helps with the stability. It guards against it. So that addresses in some way the first challenge. Okay, then we carry on. So now I can think of my predictions. Since T is just D times C plus some noise, well, I know then that my data is assumed to have a normal distribution with mean D times mu and variance sigma squared I plus D sigma D, okay? We will need that later for something. And I can make a prediction at a new point X star. I can predict T star just as C transpose times D star. D star is just all the data point, all the basis functions evaluated at the new point X star and so on. And we have the univariate normal distribution for these two. So, okay. And we can carry on. Now, how do we actually calculate that? That is, we maximize the marginal likelihood of the probability of the data given the model. So we want to find out how probably is that I do get the data given my D, my design matrix, my coefficients alpha, and not coefficients, precisions alpha, and sigma squared. And we got rid of the C by just integrating it out and so on. So that is, yeah, it's a bit of a long formula, but that's the marginal likelihood of the data. So if you now look closely, you have an interesting matrix there, which is just weighted sum of an outer product. So that's what I've found quite interesting compared to other papers. So it becomes quite simple. Outer products you can also calculate quickly in computers. So, and if you call that matrix in the exponential there, C, so it's sigma squared times the identity matrix and then the sum of the outer products. then you can write the logarithm of the likelihood quite easily like this. Okay. And then we want to maximize it. Well, you just differentiate it and set it to 0. The trick now to do is you just single one basis function out. And so on. So you write, you split 1 over alpha I di transpose off the matrix C. And then just to make notation, first of all, a bit easier, we call di transpose times that split of matrix di Si and di transpose the split matrix times TQI. There is a reason behind it, and so on, which I will come back later, why they are called like that and why it's quite useful. And then you can, yes, the derivative with respect to alpha I, because we split it off, we can just look at it individually, becomes that expression, which is the inverse of, oh, there we are. The inverse of a square, then Si minus Qi squared, and then this one is also definitely positive. So the derivative will be positive if this is positive. And so that means we will just keep going upwards. And in that case, that is the first case, if it's possible, positive, the maximum actually lies at infinity. And remember what I said, if alpha I becomes very large, the distribution becomes peaked. And it actually becomes peaked at 0, which means we do not need that basis function. It doesn't contribute to our model. And if Si minus Qi squared is less than 0, well, then we first go up towards the maximum and then down away again from it. And we can find where it's actually maximum. So we can choose an optimal alpha I. And what happens in practice is that many alpha I actually become infinite during maximization. And yeah, and the corresponding distribution becomes infinitely peaked at 0. Okay, now how this actually worked in the first instance was you started off with the whole design matrix and then you pruned it off of the things you don't need. But that is actually takes quite a long time because if you have a lot of data and a lot of functions, the matrix is large. So the whole idea was then to actually do it inverse and so on. So what the fast relevance vector machine does is we initialize with one single building block and set all the hyperparameters, alpha I, the precisions, notionally to infinity. And then we choose one of the building blocks, di, where if we set the hyperparameter to the optimal value, given the current model, because they are all interdependent of each other, gives the largest increase in marginal likelihood. And then the model is updated accordingly. And then we get an algorithm where we add basis functions if di is not in the model and the alpha I is finite. We delete it if di is in the model and the optimal alpha I is infinite because we don't need it. Or if di is in the model and the alpha I is already finite, then we re-estimate the value of the alpha I. Okay, and then, yeah, then it should be a little movie to see it in working, just a tiny little toy model. So, yes. Let's just loop this. Yeah, so it ends up with, actually first it estimates 0 and then it does a constant, just an average, which is, and then it starts adding functions in and out until it arrives at just a few and so on. And it's really just a little toy model, okay? But so that you see it in action. Okay, and I put that away again and go back here. Yes, okay. And that is just where it ends up with, so on, just a few basis functions. And one thing you might have noticed is that the functions I chose are actually really similar to each other, which would cause problems. So if you start with the whole set, because it just becomes too similar. But now we come actually how we guard against it, and it's intrinsic to the algorithm, how we guard against things. It is because actually the QI, the little QI is here, but I can also define large QI as being the basis functions times the whole matrix of inverse times outer products times T, and so on. So if alpha is currently notionally infinity, then they're actually the same. So if you let alpha I go to infinity there, you just get they are the same out. And then you can show by a bit of matrix manipulation that this inverse of C times T is actually sigma to the minus 2T minus d mu. And that's exactly the error my current prediction is doing, because d mu is my prediction from the model at the mean, and there's just the error. And then it's weighted by the variance and so on. So what it actually says is that my QI measures how aligned my building block is with the current error. If it's orthogonal to the current error, then DI will not help me at all, and so on, to improve my model. So it's called the quality factor. If, yes, I include the basis function if that is large enough. So if the question is, well, how is chosen large enough? The sparsity factor is a lot more complicated. So it's same, I define capital SI as the whole matrix, and it's DI transpose C minus 1 DI. And they are the same when it's notionally infinity. So if it's notionally infinite, then DI is not in the model, okay? But then I can say I can split it into two vectors, one lying in the column space of D of all the other vectors, and one in the orthogonal complement. So like first year undergraduates will do these kind of stuff. And then because it's orthogonal, the lengths just add up to each other. And what I actually want is if this, which lies in the orthogonal complement, is too small, then this building blocks is too similar to the other columns, and I want to avoid that. So, and what actually can happen in practice is that if you would include it, then because these are so similar, you would enter a cycle where just these things are re-estimated, but altogether, you're not progressing at all in the approximation. Okay, but how do we actually get a handle on B? So you can actually do that, again, with a bit of matrix manipulation and so on, that you can show that this B is, well, in the triangle here with right angles, it's on this side and on this side, and that length of the triangle is just the length of that basis. And on the other side, it happens to be sigma times square root of SI, and so on. So, which then means that by the law of sines, you can estimate in the end what actually B is, because B is the, well, with the sign here, you can do it that way. And so SI gives you actually in some way a measurement how different the building block is to the others. Okay, I hope that makes sense. Okay, so to summarize, we first want that that we can solve for alpha I if we want it included. So, and that is this expression here. That's when we get that we actually have the derivative negative somewhere, and we can go to a maximum. And so, or in other words, QI has to be larger than square root SI. Square root SI needs to be large enough to avoid near collinearity of the new column included. And QI indicates how well aligned it is with current error. And these things, that's a bit tricky to know how large you should choose things. So now I've only done it in the case where DI is out of the model, but you can get very similar expressions for when DI is in the model, okay? So what you then can do is, also what happens in practice is, if you have nearly linear dependent basis functions in the model, then you get wide probability distributions of the coefficients. The precision is small, and so on, because they are essentially interchangeable, and so on. What you could do to help with that, you take the whole group of basis functions and update them also always within one step, so that they can't cycle within each other. Or even more interesting, you create a new basis function from the group of functions, okay? And that's essentially what I called the second and third challenge. Okay, now a few experiments and so on. So, okay, just Lena is quite famous in the machine learning community and so on, which people come always back. So we only kept 10% of the pixels. And then we first chose the discrete cosine transform, because that's where the old JPEG is based on. And so it doesn't look very good. Then if you do Haar wavelets, then you get something out like this. And if you do Haar with different scales, well, it looks slightly better. This is Gaussian. Gaussian has the effect that it really smooths things out. And these are inverse multiquadratics. And this is just a common measure for the goodness of an image, how it's reconstructed and so on. So the closer you get to one, the better it is and so on. If you don't want to trust your eyes that you think one is better over the other. So inverse multiquadratic seems to be good. This is just now using more data. If you use 50% of the data, this comes out and so on. And then if you look in the image reconstruction world, they have all these different measurements and so on, which is peak signal to noise ratio, improvement signal to noise ratio. That's just the signal to noise ratio. And S is the structural similarity index, and F is the feature similarity index. And because I didn't really have much experience, which one should I use? So I just used all of them and so on. And somebody will tell me which one would be good to use, but it's quite good and so on. Okay, now the next challenge was new data arriving. And so that all what happens actually is we add another row to our matrix. So very simple, everything comes down to matrix calculations. You can then calculate the logarithm of the marginal likelihood of the whole data. So that's the data we had until now. And then in the last component, we just added T star in up there. Okay. And that happens to be the old marginal likelihood, logarithm of marginal likelihood, and some change in it. And the change happens to be this bit. And if you look closely, that's why I did the prediction for a new data point. It's the mean of this univariate prediction minus our actually data scaled by the distribution variance at this point of what I think it is. So it's actually it's the change of logarithm is the likelihood of a new measurement T star at X star given my current model and so on. So, and if you look closely here, so we have a logarithm there. Depending on how close T star is to M star, the whole thing, the change actually can lie between like minus a large number. I should probably have said not minus infinity because there's not really infinity. And the logarithm of 1 over square root 2 pi times the current assumed variance in our data. If it's positive, we are happy. It affirms the model. If it's negative, we actually say the model isn't good enough and so on, and it should be updated. And we can just update it by starting again the cycle of adding, deleting, and re-estimating what we have currently and so on. But there is a degenerate case. So if you think about radial basis functions, a lot of them go to zero quite fast when you get away from the center of it. And what can happen is that actually if your data point is really in a very unlucky position, you could be close to zero there or even equal to zero. So the DCT and the Haar wavelets, they have compact support. And in the next, so this would address the fourth and the fifth challenge. So new data arriving and then also updating the model. Okay, so yes. Yeah, so in the degenerate case, when D star actually happens to be zero, then all the basis function happen to vanish there, then our prediction just is zero. And it's very unlikely that the real data is also zero at that point. So it fails there. So how do we get a confidence in prediction then? And so on. And this is a bit empiric. So we let just S be a subset of samples around the new sample X star. So if X star is really far away, that is already starting to indicate a problem because we don't have really many neighbors of it nearby. And then we estimate the probability distribution of T star to be just normal with the mean, or it's just the mean of the data we chose in S. And the variance is just the variance of the data we chose in S. It also has another advantage is that if there is a lot going on in our data, if you think about an image, if you have an edge, if color changes and stuff like that, there's a lot going on, which then means that actually this one will be quite wide because we have a lot going on in that region and so on. So yes, I come back to that. Just keep that in mind, okay? And then I can calculate my expected change in the logarithm of the marginal likelihood. It's just the expectation of the change given my estimated distribution, which is here, that is just from the estimated distribution. You need to do some maths in between these two things. So if the predictive probability distribution agrees well with the estimated distribution, then the change is positive and we have confidence in the prediction. And so if it does not match well, then the expected change is negative. And it actually indicates that we need more data there, okay? And that's actually then the sixth and the seventh challenge. So confidence in prediction and informed data gathering. And I have a little example again. It's just a toy example. And so on this time, 45% of the data was kept and so on. Then I artificially use Haar wavelengths only of scale 1, which then actually I get these 0 points because they have compact support. And where there is no data, if there is enough of the gap of data, it will not try to fill in with a Haar wavelet. And so I have artificially made this degenerate case. This is now the scaled absolute difference. So of course it picks up the zeros very well, but I don't know what my real data is, but I can look at my expected change in the marginal likelihood. And there are some areas where it actually says, oh yes, I'm good. I'm at 1 here. It's scaled because, because you get quite a large range and so on. But then it picks up quite nicely the holes and so on, where it says you really need more data then. And this is then, if I just do 5% more samples, I get a much better reconstruction and so on. So it's not much more I have to do. And yes, FSIM has also nicely increased. You could also make it non-degenerate by including Haar wavelets of scale 2, then you don't get the holes, but you actually don't get that well and in the measurements. Okay, and then because I mentioned neural networks, and bit of my peak thing is that neural networks are now used everywhere, but we don't actually know what is going on with them. They're just too large and so on. This algorithm you can write as a neural network, because what a neural network does from one layer to the next layer is it first does a matrix multiplication. So in this one, we just calculate D transpose times that vector T. And so on. The normal neural networks have an activation function, which we don't actually have here. Then the next layer, we multiply by this matrix and by sigma to the -1. So no, we multiply by sigma the multivariate matrix and by the inverse of the assumed variance. By the way, this can also be estimated, but I did not do that, including that. And then you get another, that's how you get your mu. And then you get another multiplication by D. And what the interesting thing is, this part in red, actually that changes in size because you add and delete basis functions. So it keeps going in and out. So that's just that bit. And where we are at the last challenge, just as a thing, when you have actually, you're restricted by compute power and update and downlink. So I took as an example some satellites, even though they are now putting chips with processing power, quite a lot of processing powers on satellites. If you only had limited processing power, what you could do is you build a probabilistic model and it's sparse. So all your satellite actually needs to carry with it or receive is the sparse model. And then it gathers more data and it compares the data to the sparse model. It's this whole thing, how does my marginal likelihood change? And it only if it's within the model, so again, you need to set what you're accepting, what is good enough. It will only transmit data which actually disagrees with the model. And then depending on how big the disagreement is, you either alert to an anomaly, where it's then normally a human does something, or you just say, I'm updating the model, and then you need to do is update the sparse model, and you can go round and round like that. And in practical terms, you could think, we would like to know where icebergs are. That's an important thing in shipping. And they are actually quite difficult. They are easy to spot if you're in open water. But if you're already with sea ice, then it's quite hard to spot. So you would like to have a model. How do I spot this iceberg in these conditions? And then you could alert to an anomaly, and then a human would say, yes, I think that is an iceberg, so we better alert things. Okay, yes. So yeah, so that's the conclusion then. So we have strategies for stability. We have a sparse, flexible framework with probabilistic and intuitive meaning. I do like that. And we are capable to generate and include new dictionaries if you get new insights. One thing which makes humans still superior to machines is they can reverse their opinion. They can change their model in some way. A lot of humans don't, but at least the possibility is there. You can incorporate new data. We have a confidence measures. I get guidance with the data gathering process where we would like more sensors, for example, and you could do it for suitable up and down link width. Okay, and then last slide. Yes, if you want to know about this, it's written in my book, but there is, I'm supposedly working on a new edition, so you don't want to rush out and get it. But like a lot of college libraries already have it, and the library here has it, and there's an ebook also, so you can have it. And there's also a numeric analysis one. And I try very hard to build things up from the ground up to keep things simple, so because I like that. Okay, and I think, yes. So I don't know, how am I for time? So, if you, I can tell you a tiny little bit about my piece about neural networks. Would you like to hear that? Okay, so if you haven't heard about it, the MNIST data set is 60,000 images of handwritten digits, which the US Postal Service gathered. And one thing which you do quite often when you get students to start working with neural networks, you say, well, program a neural network to distinguish them. And then a lot of students go about and start coding it and give it a lot of neurons because they know that it will work then. But the real challenge you should give your students is how many neurons can you get away with and so on. And that is just a standard autoencoder. That's the simplest neural network you could think of. So, okay, that was a bit too fast. So you transform the data by a matrix multiplication, which is indicated by these weights into these hidden neurons. This one is just always in bias. That's just subtracting the average and so on. So that doesn't do much. And then you do an activation function, and then you already get the output. And all what happens is actually, I did it with 2 neurons for 2 digits. And this is the first, the separation of after the matrix multiplication, after that transformation. It's just a 2 by 2 one. And that is after the activation function and so on. And activation functions just pull the data apart and so on. And in the book, I've done some pictures of what effect different activation functions have in this pulling apart. I also call them similarity measures, these activation functions, because it essentially measures how similar or unsimilar are my data to each other and so on. And if you can then, you have only 2 hidden neurons, you can display what then, you can get basis functions out there. And this is the first basis, this is the second basis, and you can see a 0 and a 1 here. And that's then the bias. So when it reconstructs a new digit, it just combines these and so on, these 3 essentially. So with the bias, we get like an extra dimension in it. And this is how the original looks, just the bits of selection, and that is how it then reconstructs it. So, and that's only 2 neurons. If you do it with 3 neurons, that's how it first looks like. And then this is the pulling apart with, can't remember which activation function I used. I think it was just a sigmoid, but it's very simple. So there you can't really see that much there. That could, like we are now trying to separate 0, 1, and 2. So you could say there's a 2 here somehow. Okay, there's the reconstruction. And if you do 10 neurons for 10 digits, it's quite hard. So I've done the histograms on which neurons fire and so on. So, and you can see that, I can't remember, yes. So I think red is, for example, the number 1. A certain set of neurons fire then, that's where the whole thing comes from and so on. So, and you can then map which neurons fire and then predict what it was probably, but it's not that good yet with just 10 hidden neurons. Like if you look at the image, you can see that is not very good. One interesting thing here is, so neuron 10 fires for the digits 7 and 9, and that's in handwriting. They can be quite similar and so on. So yes, and what you all need is more neurons and so on. Yes, and that's, so what I actually want to say is less is more. Okay, that's the summary. Thank you.
Thank you very much. Now you can little time for questions. Are there any questions coming in? Away from the Gaussian.
Yes, yes, I did.
To that latent state? Or
you
moved to latent stable probability distributions, or is it something else?
I think it is. So, but the main thing is, which I probably should have said, is that it would be good if Martin Buhlmann would be here, because with radial basis functions, they have a hidden property that they minimize the semi-norm, and the semi-norm is equivalent to a certain PDE, and that PDE picks up a certain property of the data. So if you do thin plate splines, if you do that data, it will minimize the bending energy of the function in it. And Martin has well, in his book, he works out all the other ones which he did at the time. So you should keep that in mind. Also, the work Carola Schönlieb does, she can also tickle out certain properties of the data by using the right PDEs. So, but I have not done much on that. And so I just know about it. And I find it fascinating. So, yes. Yes. Yeah.
But I believe that on the talks which I listened, what I thought, 50% information. So much for that.
Mm. Yes.
The idea is, I mean, 50 pixels, 50% so much. That's 5-10%.
Yeah. Yes. Yes. Yeah, it's more of a toy example. So yes, compressive sensing does a lot of good work as well. Yes. So, okay.
Other questions?
Yeah. Okay. Yeah, yes, a real life example is, which I've seen in action, is the oil industry, when they do their measuring, where they try to find more oil, they use the sound waves. But the problem now is, like, they first, like when they looked for oil in deserts, they could just put their sensors wherever they wanted because there's just desert. But now they try to find reservoirs in very inhospitable places, also places where there are a lot of environmental restrictions. They are not allowed to build a road to get their equipment there. It has to be all carried by hand. So for them to place sensors is very expensive. So ideally, they want to get the same data, the same kind of images, but with far less sensors and so on. So that's where the interpolation then comes in. And yes, so that's one of the examples. The proof is in the pudding, because it's not just to, you don't just show them a pretty picture and say, look, I've reconstructed this. What they actually do is they put the data you reconstructed through their pipeline, and then whether it performs then well through the, it's not a production pipeline, but their analysis pipeline, that's been where they can decide whether it's good enough or not. I don't know whether they decided that it is good enough. We just gave them the thing. So, yes.
I think we should